Hi everyone, I'm Giovanni Pitillo, a research fellow at Boston Children's Hospital. Today I would like to show you how magnetic ball chains can be combined with other type of continuum robots to produce a dexterous workspace. But first, let's consider the unique features of magnetic continuum robots and how those can be most used effectively in clinical applications. If we incorporate magnetic material in a continuum robot, we can control the flexure of the robot by controlling the direction of the external magnetic field. Magnetic material has traditionally been applied directly at the tip of the robot in the form of a permanent magnet as shown on the left. Most recent designs have used magnetic particles distributed in a flexible polymer. This approach increases the magnetic volume compared to tip magnets, but also increases the stiffness of the tube. Ball chains, as shown on the right, are comprised of magnetic spheres covered by a thin polymeric skin. This design has very high magnetic volume while also being very compliant in bending because both create a series of spherical joints. This makes them particularly suitable in applications that require tight curvature and high tip force. In some applications, it is also important to be able to control the orientation of the robot tip with respect to the tissue it is interacting with. Tasks for which controlling the orientation is important include excising tissue, taking biopsy samples, and deploying tissue anchors. Even in cardiac ablation, it is important to control the tip orientation of the electrode with respect to the tissue. What we have done in this paper is to investigate the dexterity of the robot comprised of tendon-actuated tube and a telescoping distal ball chain. We can derive an overall kinematic model for this robot by combining the models for each. Ball chain shape can be derived by minimizing an energy function composed of the terms related to applied field and the field between the balls and gravity. We are subject to constraints that balls are rigid and the dipole is constant. Additional constraints arising from the ball are inside the tube being forced to follow the tube center line. The shape of the tendon-actuated tube evolves accordingly to the model derived by Rooker and Webster. It assumes that the tendon-actuated tube can be extended from a rigid sheath. Solving the coupled model would require iteratively computing the shape of the tendon-actuated tube, assuming forces from the retracted balls, then using it to compute the ball's extended shape and the forces applied to the tube. For rapid computation, we assume here that the ball chain does not deform the tube and so solve the overall shape in a single iteration. To compute a robot's workspace analytically, we further simplify the model and assume that the tube bends as a constant curvature segment and the chain forms a straight line along the applied field line. Using these simplifications, we find the full solution for the workspace on the lateral plane on the left and the front plane as the robot is coming towards us in the center figure. We use alpha and beta to indicate the range of orientation angles that the robot can achieve in each of these planes. We see in the figure on the right that there is a range of distances perpendicular to the straight sheath for which both angles span 2 pi, meaning that we can achieve full dexterous workspace in this range. We confirmed this region of full dexterity experimentally as shown here. In the lateral views on the left, we see that the robot orientation can vary continuously from configuration 1 to configuration 2 by passing through configuration 3. In the front views on the right, the robot is shown approaching the same point target from 4 orientations that separated by 90 degrees. In summary, magnetic ball chains are an effective type of continuum robots because they combine high compliance and high magnetic content. By combining ball chains with tendon-actuated robots, we show that full dexterity is possible. These features can be used effectively for applications in endovascular navigation and cardiac ablation. We have also provided analytical models with varying degrees of simplifications that can be used for kinematic control and workspace analysis.